All right, chemistry. Hey, I'm going to talk more about molarity this week. So I wanted to start by summarizing some experiments. Now, if you're in Mr. England's class, I know I didn't get your data. So hopefully your guys's, if you look at your individual trial, you can kind of line it up with this table. But what I did, anyone who tried the potato lab from home last week, when I was going through their work, I took their solution. They made sugar solutions of different molarities and then added potatoes. And I kind of sorted them from low to high concentration, and I color coded them. So anything that grew, I kind of marked green, and that seemed like tap water. You guys remember we all tried tap water. Tap water with no sugar in it did grow, so that was here. And everything up to about zero point 0.3 molar also grew, and you'll notice Hillary Barley, her solution she made up was 0.311 molar, and it had experienced no change. And then anything above 0.311 molar, so Chayton, Sophia, all the way to Dayton. Dayton had the highest concentration at 1.23 molar, so he had the most sugar in his solution uh, per unit volume. Those all shrank. And so what we can conclude from this experiment, and it's kind of useful, is that potatoes have 0.311, and I'm going to chop off a sig fig, moles, right, come back, moles of sucrose per liter solution. So I know this is a little awkward, but I did a little research. I haven't tried this. Imagine juicing potatoes, okay, collecting about 1 liter. 1 liter is, half of a 2 liter of potato juice. In that potato juice, you would have 0.311 moles. So again, our definition of molarity is moles of solute, so whatever you're interested in studying, per liter solution. So we can do some algebra with this. If we know that the molarity was, okay, and keeps disconnecting, we know that my molarity was 0.311 mole per liter equals x moles. We don't know how many moles over 1 liter. Then if I'm solving for x, I would multiply both sides. It's pretty easy if it's 1 liter. If I multiply both sides by 1, then it turns out there was 1 times 0.311, so 0.311. The nice thing about doing this is you can see some units cancel. I get 0.311 moles of sucrose. So if you could juice potatoes in a juicer, collect a liter of juice, and you wanted to know how much sugar was in it, you'd have 0.311 moles. And if you remember, I can convert one more time. 0.311 moles times the molar mass, I think it was 342.3 grams per mole. Got my calculator today. 0.311 times 42.3 equal to 106 grams of, that would be in a full liter, right? So you'd get 100 grams of sugar roughly per liter of solution. Okay, and so that was our results. It actually came out really good. This is typical. We usually do this lab in class and have lab groups create a whole series of different solutions. But for this one, since you're at home, you only had to make one. Thank you to all the people who did it. And also thank you for analyzing the videos that I put out. Hopefully, and molarity can get concentration, solutions, molarity, and when we do stoichiometry, they can get confusing. So the more practice you can do, the better off. We're kind of in our last unit. So I'm going to go through and do another kind of overview of molarity. I've got lots of demos. I'm pulling together stuff from my house. I've got orange juice and toothpaste, not a good combo, but you'll see why I'm talking about those. I've got salt solutions. I'm going to do a little precipitation reaction. So, and again, I'm going to try and keep this under 20 minutes. So if I go fast, you can always stop and watch certain problems. And the nice thing, I'm going to try and post up links throughout the week of different YouTubers who do chemistry videos. Because again, this general chemistry stuff and molarity, everyone has to learn it when you're learning chemistry, so there's lots and lots of video resources for it. So, okay, with that, I'm going to start. So a solution, okay, a solution is just a mixture. It's made up of a solute and a solvent. The solute is the particles in the solution. Okay, and when I say particles, I mean they're basically just going to be ions or dissolved molecules. They're not physically, they're not big enough to see with the naked eye. So anything that you see with the naked eye is either a colloid or some kind of a large um, heterogeneous like mixture. It's not necessarily solutions. So solutions are when things dissolve into water. Okay, and I say water, but it could be any solvent. The solvent is the bulk of the solution, and it's typically, it's what we say things dissolve into. So particles dissolve into the solvent. Right? Now, in most chemistry, right, and especially in biology, when we're dealing with living things, when we're dealing with systems that say turn sugar into energy, so plants, most solvent, when we talk solvents, we're talking water, and that's like 99%. Now, when you start doing some different chemistry, organic chemistry, and you're synthesizing plastics or different polymers, then the solvent may be something different. It might be things like alcohol or acetone. But a solvent is usually a liquid, although you can have solvents like you can have um, solutions of gases, okay, or gases dissolved in liquid. But for the most part, we're going to talk about the solvent being water. Okay, so let me just go through. I've got some concentrated orange juice. Let me make my screen a little bigger. Got some concentrated orange juice. Imagine, and it's not quite full. I think I made some smoothies. So, anyways, but imagine what's in here because I'm going to dump it into a pitcher. That this is 1 mole. Sorry, I've got it labeled. Okay, so 1 mole. And then I'm going to use about a liter of water. Now, this is not a very precise container. There's no markings. I'm trying to go with what's in my house. I could have run to the school, but again, I'm trying to do this like you guys would have to do these labs with the supplies that I have. So I've got a pitcher. Um, Imagine that I'm going to put a mark on it. Imagine that that's 1 liter. Okay, now chemistry glassware would be much more precise and would be measured with some standards, but here I'm just going to do this. So if I wanted to make a 1 molar solution, okay, I would put 1 mole of a chemical. So this is the orange juice chemical. So if I add 1 mole, okay, so there's my orange juice concentrate. So 1 mole. Usually when we're talking about like chemicals, a lot of times they come in solid form, so like a salt form. But in this case, just imagine the chemical. This is a solution, or so this is my orange juice, and I've got a jug of water. Gotta be careful not to spill on my laptop. So I'm gonna do this not directly over the laptop. And you guys can see the 1 liter line. So I would add my chemical, which is my solute. My solute is orange juice. There's lots of things in orange juice, but we're just going to call the whole thing orange juice. I fill it up to the 1 liter line. Those are bubbles that went a little past it. If I was in the chemistry lab, I would cap it, and I would invert it, and I would mix it. Okay, so put this off to the side. I'm not making a mess. Oops. This is, you would say, this is 1 molar orange juice, right? So I have 1 liter of 1 molar orange juice. That's 1 mole per liter. Okay, if I do this, let's say that this is a quarter of a liter, so 0.25. Say that this is 0.25 liters or 250 milliliters, but my concentration is still the same. These are mixed. So if I taste this, or I'm not going to do this because I want to put this in my fridge. I'm not going to drink out of this. If I taste this, they taste the same, right? They're the same concentration. They were mixed at the same ratio of moles per liter, 1 mole per liter. I've just reduced the volume. Okay, now, well, let me switch back and talk about the next thing while I'm here. You can do dilutions with solutions. So again, remember that this is 1 molar, and I've drank some. So let's say I have 200 milliliters. I'm going to write all over my glasses. 200 milliliters. Okay, hard. 200 milliliters. Okay, which is equal to, if you guys remember, move the decimal place 3 places to the left. That is 0.200 liters. Okay, so you guys tell me what would happen, and you already know the dilution process. I'm going to eyeball this. Let me go back. We're going to talk more about dilutions next week, but I want you to see what happens if I double the volume. Sure. So instead of being 200 milliliters, I'm now at, say the old 200 milliliter was there. Now I'm at 400 milliliters or 0.4 liters. Okay, so I took 1 molar solution and I just diluted it from 0.2 to 0.4 liters. Well, you guys know, is this going to taste more concentrated or less concentrated? It tastes like really cheap orange juice, right? Because it's got half the solute, okay, in there. Actually, it had the same amount of solute, but the volume is now twice as big. So what I'm tasting is half the concentration. So instead of being 1 molar, this would be equivalent to 0.5 molar. And I can show just a little preview of what we're going to do next week with dilutions. There's a formula that goes with it. So molarity 1 times volume 1 equals molarity 2 times volume 2. So if my starting molarity was 1 molar and my volume was 200 milliliters, I'm going to use it in liters just to get used to that. So 0.2 liters equals, I want to know what my new molarity is, and my second volume was 0.4 liters. If I want to solve for that, I would divide both sides by 0.4 liters. This is just a little algebra. Okay, these cancel, and I get molarity 2 equals, by solving it out, I can do this one in my head, I think, 0.2 divided by 0.4, well, that part comes out to 1/2, right? And so 1/2 times 1 comes out to 0.5 molar. So oops, that's a really bad end. In my cup, I now have 400 milliliters or 0.4 liters of 0.5 molar. So I had started out with half the volume, but I diluted it, right? It cut the concentration in half, but the total amount of orange juice particles in there stayed the same. They're just more spaced out. Okay, so I've got a problem a little more related to that. I'll come back to this one in a second. Do this one together. Let me zoom in. It says how many moles of copper 2 nitrate? So this would be like more of a traditional chemistry question. This would be something that's going to show up on the Willamette Promise test. How many moles of copper 2 nitrate are there in 250 milliliters of a 0.1 molar solution of copper nitrate? Okay, so we can solve this. So here's our equation. I'm going to abbreviate it. Molarity is always equal to moles over liters. Okay, so that would be something, if you're taking notes, you would want to write down for the definition of molarity. A molarity is a mole per liter. So I plug in what I know. It says how many moles, so we're going to be solving for moles. Okay, so I could put that on the top of the fraction. Are there in 250 milliliters? That's equal to 0.250 liters, which would be the bottom. Oops, 0.250 equal to, and I know the molarity of the solution is 0.1 molar, so that would be on the left side, 0.100 molar. Okay, and so if I'm solving for moles, I would multiply both sides by 0.250 liters, 0.250 liters. Okay, cancel. we get X equals, and 0.1 times 0.25 comes out to 0.025 moles of copper to nitrate. Okay, so again, in 250 milliliters, if you want to visualize this, here was our, let's say you had a big graduated cylinder. Here's 1 liter. So 0.25 liters would be down here. Copper nitrate, you guys remember, is blue, right? Most copper solutions are blue. So here I have 250 milliliters of copper nitrate. It's 0.10 molar, or remembering that that's moles per liter. So had I had a full liter up to the liter, it would have had zero point 0.1 moles in it. But since it's only a quarter of a liter, or 250 milliliters, I have 0.0250 moles of copper nitrate. Okay, now if you were to zoom in with a really, really good microscope, a microscope that we don't really have because we're not going to see individual molecules or individual ions. But if you could, what would that solution look like? I'm going to come back to the next question in a second. What would that solution look like? You would have, floating around in that box, you would have copper ions, big, okay? So, and I could draw those as little dots. I'm going to make my box bigger. So you'd have these little copper particles floating around. Draw 3 of them. You'd have moles upon moles of them. Again, remember moles, right? Have Avogadro's number worth of that particle, so 6.02 times 10 to the 23rd. I'm just going to draw 3. And then when copper nitrate dissolves, you guys can see the formula for every copper, right? Because of the charges, there's 2 nitrates. So nitrates are a little blob, it's a polyatomic ion. There's 2 nitrates for every 1 copper, right? The ratio 1, 2. So if I was drawing this representation of the solution, I would put in a nitrate, NO3 minus, NO3 minus, NO3 minus. I need 6 of them. Okay, so floating around in that copper nitrate solution, I've got these particles. I've got lots and lots. I've got, well, we figured out how many moles. I have 0.025 moles of copper nitrate. Okay, well, that's a bunch of copper, and that's twice as many nitrates, right? And so that ratio in the chemical formula tells us the number of particles floating around in that solution. Okay, so we can take this one step further. So going back to the macroscopic level, this big level, the question that you could ask is how many grams of copper nitrate? So if you want to think of this, when you evaporate solutions, I could take this and I could either filter out the water with reverse osmosis, or I know it would be really gross, but if you put this out in the sun, not only would it oxidize and spoil, but you'd be evaporating off the water. So if you could evaporate the water off the solution, same thing with the water and copper nitrate, how many grams of solid copper nitrate would be left, right, at the bottom of that flask once all the water's gone? So if we know how many moles, then you can just go from moles to mass using the molar mass. So 0.0250 moles Q32 times, and I'm going to cheat and look up the molar mass so that I don't have to add it up. Why it's doing that? Copper 2, great, has a molar mass of 187.6. Okay, 187.6. Okay, so there's molar mass. So I multiply. So let me get that out. 0.025 times 187.6. So in that, I'd have 4.69 grams. Again, that's in our original solution. So in 250 milliliters, right? Which is probably about a cup, a little over a cup of 0.1 molar solution, you would have a total of 4.69 grams of copper nitrate. Okay, and we just talked about this one. In that solution, are there more moles of copper ions or nitrate ions in solution? Just looking at our little picture, there's more nitrate because the 2 plus the 1 minus ratio 1, and this was nitrates, NO3 minus to copper 2 plus. You need 2 nitrates for every 1 copper. So in that solution, right, nitrate would be present in a greater concentration. So chemists use concentration to express how much stuff is in a volume. Okay, so and we again use the term molar or molarity. A molar is just the shortened version of molarity. So you're gonna hear me switching between it a lot. So let me write it. Molarity equals moles per liter, and you can call it molar or capital M. So, oops, molar. Okay, so all these things are essentially equivalent in terms of their unit. Okay, I would say most common in Willamette Promise chemistry, you'll see the capital M, but don't forget capital M always means moles per liter. All right, now let me do some more demos before I do some calculation. I wanted to go back to the saturated versus unsaturated solutions. So maybe you guys have seen this before, but you can dissolve certain chemicals into water fairly easily. Like here, I think I have Epsom salt, so magnesium sulfate. I just put a little bit of Epsom salt in this one. Here I have silver nitrate. I don't know why I have silver nitrate at my house. Okay, I do. I was gonna try and coat some fishing lures in silver, so I had bought some. But anyways, I used it for the lab. Um, and then this is Epsom salt again, except this time I've kept adding Epsom salt, okay, until I basically added it and it stopped dissolving. So what this is, now there's solid on the bottom, but this liquid up at the top, this solution, this is filled with so many Epsom salt ions, magnesium and sulfate. There's so many magnesium and sulfate ions dissolved in our solvent. The solvent can't physically take or accommodate anymore. So no more will dissolve and it stays as a solid on the bottom. So this solution is saturated, whereas this solution could take more, and so that's unsaturated, right? And so depending on the chemical, there's different saturation limits, and depending on the temperature. So we're not going to talk a lot about that yet. Oh my goodness, I am getting so long. Okay, so one more question, and then I've got to stop for now. I was going to show you some toothpaste. I'm going to save that. You guys see different ways to express solution, or sorry, concentration. Go to the larger this one. They list this as 1.1% sodium fluoride or 10% xylitol. And so they use percentages. So we'll talk about percentages and concentration.